Okay, we're going to move on to the next topic is going to be composite pavement technologies, right? Right, Kurt? Kurt Smith, PE with Aptech. Kurt is a program director at Applied Pavement Technology, or Aptech, and has nearly 35 years of experience in the pavement engineering field. He is currently leading several FHWA outreach efforts in the areas of composite pavements, pavement sustainability, and concrete pavement best practices. So with that, Kurt.
All right, thank you, and good afternoon. I was expecting Larry to come up here, but I guess we're going to leave Larry holding the bag, because if you're following along in your hymnals there, you see we're struggling a little bit on the time on the agenda, right? So it's now Larry's problem. I'm just passing the buck. We'll leave it to Larry to clean up the mess. Either that, or maybe Larry and I could just talk about each other's presentations and see if we can kind of wing it and see how far we get. That would be exciting. But anyway, I appreciate the opportunity to be here. I've actually had the opportunity to present here on a number of different occasions. It's always been a great conference, a great event. John does a great job pulling this together. I last spoke here in 2015, actually on this same topic, composite pavements. And at that point, the project I was involved in was just getting started. It was just starting to get some traction, and I was just kind of sharing that, some of the work that was planned at that point. Now here we are 4 years later, and we're winding down the project, so just wanted to kind of take the opportunity to share a little bit of that project with you, let you be aware of what some of the different things we were doing, some of the different things we accomplished. This was a project that was being done for the Federal Highway Administration in cooperation with SHARP 2, so it was an implementation project. SHARP 2 was a major research program that was performed in the early 2000s. They followed that up with an implementation effort to try to help implement and use some of those results and get them into the toolbox of a lot of different DOTs. So here's just a quick look at what I want to cover here today, kind of just a general outline. Some of these concepts maybe of composite pavements might be a little different than what some of you are used to, so I do want to spend a few minutes just to talk a little bit about what these composite pavements are and what they're trying to accomplish. I do want to start off though by saying that when we're talking, at least in this presentation, when I'm talking about composite pavements, I'm not talking about overlays. I'm not talking about what we normally comes to mind when you think of a composite pavement structure. That's an asphalt overlay that's been placed maybe on an existing concrete pavement. What we're going to be talking about here are composite pavements that are built as composite from day one, from the get-go. And we'll look a little bit more about that in just a few minutes. In fact, we'll talk about it right now. So essentially, when we're talking composite implies multi-lift, multi-structures. And these are pavements that are designed for long life, for rapid renewal and optimized performance. And we'll get into some of the specific benefits. One of the big benefits that they offer is a sustainability component. We'll talk a little bit about that. But sustainability, as many of you know, is starting to gain a lot of traction in many parts of the country. Many areas are starting to become more cognizant of sustainability and what it means and how it can affect some of the things that we're doing. So we'll talk a little bit about that. And in this in this level, what we're talking about then are either new hot mix asphalt pavements that are placed on new concrete pavements, and we'll just call that HMA over PCC. Again, not overlays, this is new construction, or something some of you may be familiar with, hot two-lift concrete pavement. So this is 2 layers of concrete placed on each other in a wet-on-wet type of process to promote bonding between those two layers. So again, not overlays, but structures that are designed this way from the get-go, from day one. If we look at the composite pavement systems, HMA over PCC, we'll construct an underlying concrete pavement structure. This could be a jointed plain concrete, maybe even in some cases a continuously reinforced concrete pavement structure. that is designed to carry the bulk of the traffic loading. So it's almost designed as the same structural thickness or perhaps the same structural capacity as it would be by itself. But what we're going to do is we're going to top that with an asphalt pavement structure. That could be a stone matrix asphalt, a polymer modified asphalt, maybe a conventional warm mix or hot mix asphalt surface that is optimized for the design conditions. Maybe this particular pavement or that particular structure has some certain design elements that are very important. Maybe it's important that it have a high level of friction. Maybe it's important that it have an extremely high level of smoothness. Maybe it needs to have reduced noise emissions. Whatever those conditions might be, that surface can be optimized for those specific design conditions. Typically, what we might be looking at, that underlying concrete slab might be anywhere maybe 7, 8, 9, 10 inches thick. That top surface of that asphalt topping course, maybe 1 to 3 inches, somewhere in that ballpark. So that's new composite HMA over PCC. The other composite pavement type, PCC over PCC. This is, again, now 2 distinct layers of concrete. Now this might be a little difficult, maybe something a little different to wrap your head around here a little bit, but it is 2 layers of concrete that are placed wet on wet, and by wet on wet I mean after that first layer is placed, before it hardens, before it gains all of its strength, while it is still semi-plastic, we're going to follow that up with the top layer. And the idea is by doing that so quickly and so rapidly and in this wet-on-wet process, we're actually able to achieve and promote a good bond between those 2 individual layers. We say, well, why don't we just do that with a single lift? Well, what we have the opportunity, if we do this in a 2-lift type of situation, we can, in that lower lift, that's not going to be exposed to any significant environmental effects, maybe any of the traffic loadings, we can take the opportunity to maybe economize a little bit and maybe we use some reduced cement contents in that, maybe some certain aggregates, maybe recycled aggregates, maybe marginal aggregates that may not be otherwise suitable for use in the surface. We can use those in the lower lift to kind of help provide some economy, and there's also some sustainability benefits associated with that as well. But that bottom lift is typically going to be the thicker of the 2. It'll, again, be somewhere in the order of that, maybe that 7 to 10 inches thick. Then we'll top that with a thinner surface layer, somewhere around 2 to 3 inches thick. That'll make use of the higher quality aggregates that, again, have been, and that lift will be optimized for the particular conditions, whether I have certain friction demands, whether I have certain noise emissions that I need to try to meet. We can optimize or tailor that mix design in the top surface to try to meet that or to address that. So as a system, as a unit, this thing is providing us a number of different things, right? This is great because I can use less cement, I can use lower quality aggregates in the lower lift, saving money, being more sustainable, and just where I need those high quality materials, I can focus those on in the upper part of the pavement structure and be able to receive those benefits from that higher quality concrete that's placed in the upper lift. So that's just a quick introduction to what we're looking at with these composite pavement structures. So then the question is, why is there the interest in this? And well, there's a relatively new interest. It's really not that new, and in fact, we'll talk a little bit about that. Some of there's a long history of use of 2-lift pavements that actually goes back to the very earliest days of concrete pavements, and we'll talk a little bit about that. But again, some of the opportunities here, some of the benefits. We have a surface that is optimized for the design conditions and can be optimized for friction, smoothness, noise, whatever. We have a surface that can be very easily renewed, whether it's either an asphalt pavement or that concrete pavement can be retextured to help achieve the smoothness or the friction requirements. These can be designed as long life pavement structures. They can be designed for 30, 40, 50 years or more. And then we mentioned before that the sustainability really comes into play and is a big aspect of these designs, because we have the opportunity in those lower lift, whether it's the asphalt over concrete or the 2-lift concrete, we have the opportunity to make use of maybe some local aggregates, local materials, maybe certain recycled aggregates, recycled materials that obviously have lower costs. But also, if we're able to use some of those local materials, we don't have to transport in higher quality materials, and there's a cost associated with that. There's also a sustainability cost of having to truck in some of those high quality materials. It takes fossil fuels. There's a footprint, environmental footprint associated with transportation of all of these materials. There's an environmental footprint associated with mining those high quality materials. So if we can make use of local materials, recycled materials, there's some significant environmental benefits. We also mentioned the reduced cement contents that we can use in some of the lower lifts as well. And essentially by design, by definition, long life pavements are sustainable. Nothing is really more sustainable on a pavement than not having to do anything to it, right? That pavement lasts 40 or 50 years with very, very minimal maintenance. That is a very sustainable pavement structure. We already mentioned some of the benefits associated with the reduced carbon footprint. And in the right environment, this can be a very cost competitive, these can be cost competitive designs. And a number of agencies have been able to realize some significant cost savings with these. So there's a number of factors or potential benefits associated with these structures. And there's a number of agencies that have experience with this. And this only goes back maybe for about the last 15 or 20 years of different agencies that have experience with these types of composite pavement structures. The brown or tannish color is the HMA over the PCC composite. The light blue is the PCC over PCC or the two-lift. So you can see a number of different agencies. And you're probably all looking at that Pennsylvania one, and you will say, wow, Pennsylvania's colored in there. We'll take a look at that. And actually, George mentioned it briefly this morning in some of his remarks in this morning's presentation. So let's just take a few minutes to talk about HMA over PCC composite pavements. There is a strong history of use of these pavements in Europe, particularly Germany and the Netherlands have a strong history of performance and actually have documented some outstanding performance from these pavement structures. But we also can boast some good use here in North America. A number of states, Arizona is one of the states that has a lot of experience, Ohio, Illinois, Texas, Ontario, just among some of the other agencies that have some experience. And again, as we mentioned previously, what we're looking for here, that concrete layer, that underlying concrete layer is kind of our load layer. It's the one providing the structural load carrying capacity. The HMA is providing kind of the functional serviceability component of our pavement structure, so providing the necessary smoothness, friction, or noise requirements. And that asphalt surface then also provides a renewable surface that can be easily renewed on a periodic basis to help renew and meet whatever those surface requirements may be. A couple of just examples. Arizona has a number of different projects down in the state that they've used this composite pavement technology. This is just one particular project on I-10 where they featured a 1-inch asphalt rubber friction course over a 13-inch pavement built in 2004. It's carried to date over 20 million trucks. Very, very heavy truck traffic loadings. And after 14, 15 years, it's showing very, very good performance with just some very low severity reflection cracking and very negligible rutting. Another project that was actually constructed under the implementation project that I'm discussing here today was on US 60 near Richmond, Virginia, on right near the airport there on the west side of town. This one was interesting because they used a continuously reinforced concrete pavement, so no regularly spaced transverse joints, heavy reinforcing steel that runs longitudinally through the length of the project. Big advantage here is the CRC without the transverse joints. It does crack, but it forms cracks that are very tight and typically maybe 3 to 8 feet apart. So there's not a lot of movement. So continuously reinforced concrete pavements in general receive asphalt overlays very well without big concerns about reflection cracking. So that's what the Virginia DOT was looking at here. So on the left side of the screen shows the placement of the CRC paving. It was done at night. And on the right shows the placement of the asphalt overlay or the asphalt surface about 2 weeks later. And this was designed for a 30-year period, about 5.3 million ESO, so not a lot of heavy traffic, but it was something that Virginia was very interested in. They'd had a lot of good experience with some of the stone matrix asphalt, so they were very interested in applying this in this particular location. And then the one in Pennsylvania. Some of you may be familiar with this project. I became familiar with it when I was out here a little over a year ago, presented up in Williamsport, and this was one of the projects that was very hot and heavy at the time. There was a lot of discussion on this. This is in the Central Susquehanna Valley Thruway. It features a 2-inch SMA and a 3-inch hot mix asphalt, so 5-inch total, if I still have these numbers right. Now, these numbers were somewhat preliminary, so there may have been some slight changes to some of these, but all of that was going to be placed over a 9-inch jointed plain concrete pavement, and all of that over either a 4-inch treated asphalt or a cement treated perm over a 4-inch crushed stone subbase. So that was at least the cross section at the time when I was out here. My understanding was it was to be paved, or at least paving aspect was to be initiated 2018. Can anyone confirm whether that paving started? It did commence. It's going on now. Okay. And I know they'd been doing bridge work and other stuff, I think, prior to that. So, all right. So this project then is something that is currently underway, and I've been working with Bob Johnson up there and working through some of these different details. So very interesting project, and certainly one of these new composite pavement structures that PennDOT is directly involved in. One of the other aspects of this particular composite pavement type that I didn't mention previously was the potential insulation effects. And this has been something that's very interesting to a lot of different researchers, in terms that we know that concrete pavements by themselves, when they're exposed to the elements, they tend to curl. As the pavement warms up or cools off, that pavement tends to curl up or curl down, in response to those temperature changes. And there's been a number of studies looking at, well, what's the potential impacts of putting a thin asphalt surface on that? Does that kind of help reduce the magnitude of some of those thermal curling effects? And this is from a project at Minroad, showing a number of different plots on there. If we just focus, I think, maybe on the temperature plots, which is the bluer ones, it shows the temperature at the top and the bottom of that slab. The 4-inch would be right at the top of the concrete slab. The 9-inch depth, it'd be at the bottom of that concrete slab. And you can see how that temperature, how they kind of fluctuate up and down, as you can imagine, over time. But then once when that asphalt overlay is placed, all of a sudden the magnitude of those cycle curves kind of flattens out a little bit. So what we are seeing is there is some reduction in some of the curling effects due to the placement of that asphalt surface. And that potentially has a big impact on design, because what we're seeing in some of the new AASHTO pavement ME, that thermal curling effects can very significantly affect concrete pavement performance. So this potentially could help contribute to the longevity of that underlying concrete pavement slab. I mentioned previously about reflection cracking, and that is a potential concern anytime you're putting asphalt on a concrete pavement. We see the picture on the far right-hand side there. That's what we can get, those transverse joints in that underlying concrete pavement. They're moving not only horizontally, they're moving vertically under traffic loading. They can basically just shear through that asphalt surface. So that is a concern if we're going to be doing that from the get-go. We see that potential issue on our asphalt overlays of existing pavements. What's going to happen if we do that from day one? Well, what we can try to do is from day one, try to maybe apply some mitigation treatments, or something that the research really showed very strongly was the effectiveness of using sawing and sealing procedures. In other words, matching joints in that asphalt surface precisely above the joints in the underlying concrete pavement. Sawing those joints at that location, and effectively what we're doing is we'll say, yeah, it's going to crack, but we're going to make it crack right here where we want it to, and now we're going to be able to control it and maintain it. It's going to be a nice straight crack. It's not going to be all jagged and spalled out. It's going to be nice and straight, sawed, and we're going to saw it, we're going to seal it, and we're going to maintain it. And this seems to be a very effective way of trying to deal with or address some of those potential reflection cracking concern. Or the other alternative, as some agencies have looked at, the use of CRC. Again, these continuously reinforced concrete pavements that don't have regularly spaced transverse joints. They are very receptive to receiving concrete or asphalt surfaces. A couple of quick things, just as we did some of the different pilot studies, pilot implementations of this particular technology, some of the things that kind of jumped out. When we're placing those dowels, make sure those dowels are placed at the mid-depth of the concrete and not the mid-depth of the total composite pavement thickness. For the concrete smoothness, we don't need high levels of smoothness since it's going to be overlaid, but we still want pretty good levels of smoothness because that's going to help us achieve higher levels of smoothness in the placement of that asphalt surface. PCC texturing can be done using pretty much agency standard, and what that does is help promote a mechanical bond then between that existing concrete and that asphalt topping surface. Curing, we still need to cure that underlying concrete pavement using your agency standard materials. Concrete joint saw cutting, pretty much do that again with your agency standard. This can be just a single cut, 1/8 of an inch saw cut to typically the 1/3 of the slab thickness. Then when we get into the placement of the asphalt surface, we use a tack coat just much as you would if you're placing an asphalt overlay, again to help provide in this case some chemical bonding between the two layers. And then we get into the sawing and sealing, and this is where it's really important that we adequately mark the locations of those joints in the underlying concrete pavements. That can be done with paint marks. Some agencies have actually used some pluggers, some PK nails, where they place those outside of the paving zone, very accurately located, and then they can snap a chalk line across there to help establish the saw cutting line. It's very important that we get those located within about 1/2 of an inch or so of that underlying joint. If there's any significant deviation, you potentially run the risk of developing two parallel cracks, which could then cause some significant performance issues. And again, depending on the depth of that asphalt surface, the depth of those saw cuts could be anywhere between maybe about 5/8 to maybe an inch and a half. So that's the asphalt over concrete. Let's look a little bit at the concrete over the concrete, or the two-lift. There's, again, a strong history of use in Europe. We actually have a strong historical use here in the United States. Some of the early concrete pavements in the early 20th century, the early 1900s, actually used two-lift pavement structures. A lot of the jointed reinforced concrete pavements that were placed in the interstate era also were built using two-lift. Not so much for sustainability at that time, but more for that at that point to accommodate the placement of the welded wire fabric reinforcing that was commonly used in those designs. So again, this is done in a wet-on-wet process with two different paving materials as we described. So again, what is the concept? This is what we're trying to accomplish. We're placing these two different layers, a bottom lift, maybe 6 to 9 inches, using maybe recycled materials or more marginal materials, topped with a higher quality durable aggregate. If we do that in a wet-on-wet process, the end result will be essentially a monolithic pavement structure that behaves monolithically as a single unit and not as two separate concrete pavement structures. Quickly, a couple of different projects that were constructed under this FHWA implementation study. A project on I-65 in Nashville featured a 3-inch top lift over a 10-inch bottom lift. The main driver here was they had a lot of soft limestone aggregate that was suitable for concrete but was not suitable for use in the surface because it was very polish susceptible. So they wanted to be able to demonstrate that they could use that polish susceptible aggregate in the lower lift, and then they hauled in the higher quality polish resistant materials that they used in the top lift of the pavement structure. Another project on I-210 near Los Angeles. This was a 3-inch top lift over a 9-inch bottom lift. And they actually looked at two different sections in the lower lift. One that featured recycled concrete aggregate, and this was actually concrete aggregate that they reclaimed from the actual construction project. So they demolished the existing concrete and then hauled it off, crushed it, processed it, and used that back in one segment of the bottom lift. And then they also looked at another segment that used lower cement content. So two attempts to really try to be more sustainable, to try to reduce some of the carbon footprint. And then finally, there was another project on a frontage road southwest of Houston that was constructed in 2017. This was interesting because this was the two-lift CRC. Texas, if you're familiar with any of the paving practices in Texas, they are a big fan of the continuously reinforced concrete pavement structure. And if you look at the lower picture, which is placing the first lift, but you can see all the steel in the foreground. So there's a lot of structural or reinforcing steel. It's not truly structural steel that is laid out ahead of these continuously reinforced concrete pavements. And they were looking at using two different coarse aggregates in each lift. One which had much higher than they typically allow in terms of the thermal coefficient of reaction, to try to see what the potential effects of that, whether they could use some of those types of aggregates that had a higher coefficient of thermal expansion than they normally would allow. So that was a project that they constructed a couple years ago. A couple things that quickly came out of that, some of those field studies. The dowel bars here, we want to place those dowel bars at the mid-depth of the total concrete pavement thickness. So again, we're assuming here that it's going to be a composite thickness, that those two lifts are going to behave as one. So we want to make sure that we're placing those at 1/2 of that total thickness. One item, or a couple items, I guess, when we get into the delivery, this can be a little maybe burdensome because you've got two different mixes, so now you've got to keep track of these different mixes. Maybe you've got multiple plants that you got to keep track of. So there is a little bit more front-end work that has to be done on the part of the contractor. But it's been demonstrated that with a little homework, with a little legwork at the beginning, they can work through a lot of these issues. One of the first is making sure that you're producing the concrete in the proper quantities. If you just look at this cross section, if you're producing a bottom lift with mix design 1 and a top lift of mix design 2, clearly you need a lot more material for that bottom lift than the top lift. So you need to make sure that your plants and your productivity is such that you're going to be able to feed those different pavers. Most agencies, a lot of the contractors have employed 2 different pavers for each of these different mixes. So you got to make sure we're going to be feeding those pavers and keep them moving. The other thing is to make sure we're keeping track of these mixes. So the people that are driving with the bottom lift mix are going to go to the right paver. Again, contractors are very innovative the way they do some of this. Sometimes they set up a ribbon system where they have a certain color-coded ribbon that they'll then match that with a color-coded ribbon on the paver, so they know which paver to go to. In Tennessee, they actually had different types of delivery trucks. They had in-dump trucks with the bottom lift and front-end discharge ready mobile mixer type trucks for the top lift. So a lot of different ways you can do that, but it is important to try to keep track of these different mixtures. The placement, there's no curing compound on the bottom lift. You don't want to do anything that could impede the potential bonding between those. You do want to make sure that top lift is placed on that bottom lift Typically within less than 90 minutes. Some agencies have a specification that even says less than 60 minutes. Typically, it's been shown that if you get it less than 90, maybe in some cases less than 60, you're going to ensure that on wet paving, you're going to get good bonding. And often then the top lift will be paved slightly wider than the bottom lift. That's mainly more of a practicality thing. It's hard to get those pavers matched exactly without potentially tearing some of the edges. So typically they may go out about 1.5 inches or 2 inches or so on either side, just to be able to accommodate that second paver as it's riding over the bottom lift that has already been placed. Texturing and curing, basically done according to agency standards. The joint depth is a little different here, and the recommendation is to saw the minimum of either the upper lift plus 1/2 inch or 1/3 of the composite slab thickness or the total slab thickness. And the idea is you want to make sure that we're at least down below the thickness of that top lift, because there's a concern if we were to in that sawing right at the transition between those two lifts that there might promote some horizontal cracking. It's never been observed, but I guess it's just something that's been trying to be avoided if at all possible. So that's a little bit on the composite pavement technology itself. This, as I mentioned, was all done under this Sharp 2 R21 project implementation, which was administered by FHWA to kind of help support and promote this type of technology. And it started in 2014 and is just now starting to wrap up now. Number of different activities. We worked with a lot of these different highway agencies to provide some technical assistance as they were designing and constructing some of their different pavement structures. We were on call to help meet some of their needs and meet some of their addresses. We went out to the site and documented the construction of each of these different projects. We constructed a showcase and open house in California as an opportunity to bring in people so they could observe some of the composite pavement technology construction. We delivered a number of different one-day training courses, workshops on this technology, including 2 in Pennsylvania, one up in Williamsport about a little over a year ago, and then another one was in King of Prussia earlier this year. And then we also had a peer exchange where we brought in a lot of different highway agencies to kind of share some of their experiences with these different technologies. There's the 4 different pilot projects that we already talked a little bit about: California, Texas, Tennessee, and Virginia. These are the products that are coming out and should be available sometime within the next 2 months. These will all be available from FHWA. There'll be a formal showcase report that's available, documents that showcase that was done a couple years ago, a peer exchange report that documents the results of the peer exchange, including some ideas for implementing some of these technologies. And a lot of these ideas came from DOTs that were involved in it. So it was kind of a some ground up ideas on how to move forward with some of these. There's pilot state reports available from those 4 pilot states we talked about, and then there'll be a final report that also summarizes a lot of this. So just something I want to leave you with really quickly. There is another type of composite pavement. Just if I haven't muddied the waters already, I'm going to just muddy them a little bit more. PCC over asphalt. And this could be in new design. This could be PCC placed on an asphalt treated base. And an asphalt treated base brings a number of strong benefits. It's a base that provides good uniform support to that concrete slab. It has reduced erodibility. It's resistant typically to moisture issues. And at the same time, though, it also has a lower rigidity, so it doesn't produce some of the higher level curling stresses that some of the cement treated or lean concrete bases can sometimes produce. So there's a lot of advantages to placing a concrete pavement on an asphalt treated base. So that could be done from the new design and the rehabilitation design. What used to be called white topping, I think maybe some folks have kind of moved beyond that terminology, but to me I think it still makes sense. The white topping is basically placing a concrete on an existing asphalt pavement structure. We can do that what I call either conventionally, and it's somewhat artificial, the distinction here, but roughly greater than about 6 inches I call as a conventional design, thin less than about 6 inches, where typically if you're going thinner than 6 inches, you may have to bring in some reduced joint spacing considerations to kind of help control some of those curling stresses. And the other aspect, I guess, for all of these, particularly probably for some of the thin ones, is that it does require that you have sufficient thickness, asphalt thickness, to help provide or help carry some of the structural loading, and that asphalt be in somewhat good condition and not be showing a lot of deterioration or not be exhibiting some stripping or anything like that could detract from the load carrying capacity of that asphalt. You're not looking at that asphalt to be the only structural load carrying member, but you are looking at it to help provide some structural load carrying capacity. So just a couple of examples then of some of these types of composite pavements. A couple of overlays on the left-hand side, US 1 in Florida, which I call a conventional white topping. That actually has been down for almost 35 years or more. It has been showing outstanding performance. A relatively newer project in Illinois on I-72, a thinner white topping, and you can kind of see some of the shorter joint spacing that they've incorporated in that project. And then a project up on the Illinois Tollway on I-90 that utilized an asphalt-treated base in a new pavement type of construction. So with that, just to quickly summarize, the idea here was just to, if you haven't been exposed to it already, just to introduce some of the composite pavement structures. And again, the main thrust here was composite pavements from a new design standpoint. Talk a little bit about the characteristics and some of the potential benefits. A number of different agencies have constructed this in recent years, and I think there's the potential with the many different benefits associated with this. I think a number of agencies are going to start looking at this harder, and I think there's an opportunity for more and more and greater use of these different composite pavement technologies as we move forward into the future. So with that, I have no idea how I did on time. I probably screwed the pooch, I guess, on time, Larry. I'm sorry. But if there is time for a question or two, I would be happy to take it.